we now introduce the topic of work. We're done with forces for now, all right? But we're actually going to see how force, now we can use that concept of force to introduce the ideas of energy, all right? And to introduce the ideas of energy, we introduce this term called work, all right? Now, before we actually get into what work is, we need a little bit of mathematical background. So we're working with vectors, of course, and when you're working with vectors, you can add vectors. We've seen how to do that. You can also multiply vectors, and there's a few different ways that you can do that. And one of the ways that you can multiply vectors is known as the scalar product or the dot product, all right? So the dot product is the way to multiply two vectors together and the result becomes a scalar, okay? So there are a couple of definitions of the dot product. If I have two vectors, A and B, and when I have vectors and I have a dot here, I'm implying vector multiplication. It's not just the regular multiplication dot. This is now the vector dot, okay? And so if I have two vectors, A and B, and I dot them into each other, that's equivalent, and technically I should put absolute value signs here, all right? If I dot A and B together, what I'm doing is I'm taking the magnitude of A and I'm multiplying it by the magnitude of B, and then I'm multiplying that product by the cosine of the angle between the two vectors, okay? So theta is the angle between the two vectors. Another way of achieving the dot product is to simply break both components up into their x and y and z components, however many dimensions you're working in. And if I take A dot B, then it's essentially saying taking the x components and multiplying them together, ax times bx, and then I add to that the components in the y direction multiplied by together, and then I add to that the components in the z direction multiplied by together, all right? And so what I can do is simply then sum up these numbers and I get just a number. That's why we call this the scalar product, okay? The dot product is often known as the scalar product. There's another way to multiply vectors together that gives you another vector, and that's the vector product or the cross product, and we will run into that when we get into rotational motion and then magnetic fields down the line. But this is the first way to multiply vectors together, and this is known as the dot product. And it's really this definition or this rendition of the dot product that is going to be useful for us, okay? It's going to be useful for us. Now, with this mathematical background, and keep this definition of the dot product in your back pocket, we're going to need to know this maybe sometimes, okay? This is more of a mathematical definition, all right? This is more of a mathematical definition. This is the working definition that we'll use, but we may see this down the line, all right? So, how does this product help us define work, okay? So work, at the end of the day, is not something you come home from, okay? When I was a kid, work was what my dad went to in the morning and came home from in the evening, but in the physics sense, work is done when you apply a force on an object and that object then moves, okay? So let's say that I have a block, right? And that block, I apply a force to the block, I apply a pushing force F, and the block then moves from here to say some distance down, and the block finishes here, right? So I've moved the block a distance delta x. Mathematically and in the physics definition of the term work, we define work to be the product of force times displacement, okay? When we're working in one dimension, we define work to be the force times the displacement. And you can already kind of see where this is going. Now, work is a scalar, okay? Work is just a number. It doesn't have direction. It only has magnitude. But force is a vector, and displacement is a vector. So this is already a vector times a vector that gives us a scalar, which is what the dot product is. Now remember that I said the A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. If I apply a generic force in any direction, okay, so let's say that I apply a force to my block. Let's say that my force, instead of being applied directly along the direction of motion, let's say that I apply a force in this direction. But the force doesn't actually cause the block to lift up off the ground. This may be the case of maybe carrying some luggage at the airport with a handle at some angle that you can pull out of your luggage, and then you're pulling it alongside you out of the back. You're not lifting it off the ground, but you're just pulling it off at some angle, and it's rolling across the ground. So this force is not necessarily lifting the block or your luggage or whatever the case may be off the ground, but it is pulling it in this direction. Okay, so this is actually the direction of motion, what we call the DOM, right? That is actually the direction of motion, but your force is in this direction. So in this case, what is happening is that because delta x is still going to be along the x direction, right? However far you pull it is delta x, there's going to be this angle between the x direction and the direction that your force is pulling in. And so this is known as F sub x. So in this case, your work is equal to the force in the x direction times delta x. And again, these are vectors. But what is Fx in relation to F, right? Well, they're related through the theta here by the cosine component. So Fx is equal to the magnitude of the force F times the cosine of the angle that the force makes with the horizontal. So this is the magnitude of your force F times the displacement delta x times the cosine of the angle between them. And now we can see that the work is equal to the magnitude of the force times the magnitude of displacement times the cosine of the angle between them. And this is the definition of the dot product. So what we can conclude is that the work is equal to the force dotted into delta x. So if I know what my force is, and I know the displacement that I've moved my object, then I can calculate the work done. Now there's a very subtle point here that needs to be made, and that is, I must move the object. If I do not move the object, no work is done in the physics sense, okay? So I must cause some displacement or else I have done no work, no matter how hard I push. So for instance, I can push all day against the whiteboard, which is attached to a cement wall. I can push and push and push, but if that board does not move, if it does not move, which it's not going to because of the cement wall behind it, then I have done no work in the physics sense, okay? So you must have some displacement for the work to be done. Now, you can see that work is equal to the force times the displacement. And this holds for a constant force, all right? This is the definition of work for a constant force. But what if your force is not constant? What if your force is some function of position, okay? What if your force is some function of position? Well, if your force is some function of position, what you can see is that the work is going to be equal to the force as some function of position dotted into delta x. But if force is some function of position, it's not just a constant value, then the amount of work done over each tiny increment delta x is going to vary over the course of the path. And what that means is that what I need to do is then add up all of the little tiny chunks of the product here over each tiny chunk of delta x. So what I'm essentially going to do is I'm going to be integrating this function. So if f is not constant, but some function of x, then I need to integrate and my delta x's, as they become smaller and smaller and smaller, go to dx. And I'm going to integrate this from the initial point on my path to the final point on my path, and that will allow me to then find the total work. Okay, so that is work. But before we leave, let's talk about units. Work is going to have what units? Well, force has units of newtons, and position or displacement has units of meters. So work has units of newtons times meters, okay? Newtons times meters, and we give that a special name, all right? So newtons times meters is equal to joules, all right? So 1 joule is equivalent to a force of 1 newton on an object that then moves that object 1 meter. So if I apply a force of 1 newton to an object and I move it 1 meter, then I have exerted a work of 1 joule, or 1 joule of work has been done on that object, okay? As we will find out shortly, joules actually have the same units as energy as well. So work and energy are actually the exact same thing. Now, before we leave here, let's find out what happens here, okay? And there's another way that I can look at this product that actually allows me to move away from the force idea and allows me to then incorporate this idea of energy. And energy is what we want to get to, because energy will allow us to do away with forces, do away with vectors, and because energy and work actually have the same units, energy is also a scalar. So it actually allows us to simplify a lot of the situations that we saw with Newton's laws. All right, so in the next video, I'll show you how to derive a very certain quantity from this quantity of work, so stick around.